symmetries of the material properties. The symmetries, in terms of geometry, they can be symmetric to point, for example, symmetric to the origin of the coordinate system. This can be symmetric respect to a line, can be symmetric to a plane. So let me make one example. So for example, here we consider one coordinate system, and say it's 1 and x2 and x3 axis. For example, so say let me consider this plane, the x3 and x2 and x3 plane. Okay. So this plane, basically, let me say that is the plane x1 equal to 0. So we consider this, and say, for example, we consider two particular points in a material. So basically, this is the coordinate system we pick within a certain deformable material. So say, for example, let me pick one point. Let me make arbitrary one here. So for example, this point is here. So in let me put it into two colors. Okay. If we pick this point and the point has the coordinates something like this. Okay, so basically from here, hopefully you can see this clearly location of this point in space, and basically the lines I marked, for example, this is, say, the first coordinate, this is A, the second coordinate, this is B, the third coordinate, this is C. So for this point, these are the coordinate A, B, C in terms of this particular coordinate system. And on the other side, respect to this plane, particular plane, x1 equal to 0, is symmetric to this plane. On the other hand of this plane, we have a coordinate, for example, here, and say, let me mark here, okay? So this point is symmetric to this plane, so it has a coordinate A, and minus A, and B, and C, okay? If after we assign these the locations of the points, and we said if the mechanical properties of, let me call this a point A, and let me call this a prime. Equal to the mechanical properties at point A prime, then we said this material is symmetric with respect to the plane x1 equal to 0. Okay, so basically this one is called the plane symmetry. Okay, I just make one example here. And so what kind of the mechanical properties? I would say properties. And basically mechanical properties we can best describe is, for example, here earlier we have described tau ij equal to ij kl and epsilon kl. So the mechanical properties can be described by, for example, this one. This one last time we defined as a compliance tensors. Compliance tensor basically are components relating the behavior of the stress and strain. So linking Hooke's law, linking the relation between strain and stress, basically that is through the mechanical properties. And in our perception from fundamental mechanics of material, those properties can be, for example, Young's modulus, can be Poisson ratio or rigidity modulus. But for the more anisotropic material that have the more independent parameters. Okay, so basically that one, using this as the particular example, And because of plane symmetry, it's easier for us to comprehend. But again, if with other example, for example, if we say a point of the symmetry, the point symmetry, for example, if you have picking up another, say another example, another point, for example, minus A, minus B, minus C. So in this way, you can see the 2 points, A and A double prime, that one basically is a symmetric respect to the origin only. Okay, so for this example, A to A double prime, that is called the point symmetry. There's another example. Okay, so with those kind of the definition in mind, then I'm going to do a little bit more exercise and to begin to simplify the contents of these using a few other symmetric properties. And that will allow us to simplify for anisotropic materials. We have 21 parameters, right? So using the properties, appropriate properties, the properties of the symmetry, then we will be able to further knock down a few numbers from here. And so the whole thing, the remaining of these sections is to lead to the discussion of we call the anisotropic, anisotropic material, and then I'm going to relate to the transversely anisotropic material. And then leading to this is T, and leading to anisotropic. Material. Okay, those are the very common seen in the engineering applications, and of course we might have the anisotropic, but those ones will be more relevant to our applications. So that is the outlines for today, and maybe including the lectures in the following hour or 2 hours. Okay. So we can exercise. We can exercise the plane symmetry example. So for example, say if we will pick, say this is x1, x2, and x3 axis, and then you pick this plane. So this plane is x3 equal to 0. So we say the plane of symmetry is this. And based upon this, we want to simplify the contents of CIJKL. Okay. So for this case, you can see, again, I pick 2 points. For example, if I pick the points here, okay, so for this point, let me label this is the point A, and it has 3 coordinates, and this is the x3 coordinates. This is x1 coordinate, this is the b coordinate. So basically point A, it has the coordinate A, B, C in terms of the x1, x2, x3 coordinate systems. And on the other side, symmetric to this plane, so that one is point on the other hand of this plane would be to let me call this is the A prime, and A, B, again, is symmetric respect to the third axis, so this is minus C here, okay? So under these situations, if you would pick any point, then you can always find is the mirror location on the other side. And at any pair of the mirror points per this plane of the symmetry, we claim the material properties are the same. Okay, material properties are the same for any pair of the points that any pair of the mirror points with respect to this plane of symmetry. So based upon these recognitions and to proceed the calculation to simplify the contents, the first step we need to build up is mathematical description to describe such to describe the relations transforming from A to A prime, which means that involving the transformation of the matrix. Okay. So, for example, for A, it has a coordinate A, B, C, and in general, let me describe for general description of the coordinate system, let me call it x1 and x2 and x3. Okay. And for the similar process, any new points, let me say it has the corresponding coordinates x1 prime, x2 prime, and x3 prime. Okay, in general, before we claim, and we just simply give the general coordinates to the 2 points. Okay, now we impose the symmetry, the plane of a symmetry, so such that after imposition of such a particular relation, we know that the A prime equal to A, B, and minus C for this particular example here. This one is that we impose the symmetry properties. Okay, so after imposing the symmetric properties, then we are able to build up the relation between those coordinate systems. That is, you can observe that pretty easily. Using this as the number, the numeric example, you can see this equal to this equal to this, and this one equal to multiply with minus 1 will be equal to this, right? Okay, so based on this, you should be able to quickly, easily to build up the transformation tables describing such a particular relation. Let me put x1, x2, x3. And this is x1 prime, x2 prime, and x3 prime. Using this one, this should be 1, 0, 0, and 0, 1, 0, and 0, 0, minus 1. Okay? Okay. So with this one in mind, then basically this one is the content is our Lij. That means match to our, we can borrow from our previous, the tools, mathematical tools. Once we have the transformation matrix in place, we are able to calculate, for example, stress equal to Ij and L, let me say, Ij, II, and Ljj, right? And the same pattern applies to strain. And furthermore, we can have this one to transform the C, the tensor, the order of 4. So basically, once this one is in place, or we found this as a first step, then we can do a lot of the calculations. Okay, so today in particular, I want to, based upon this information, to see how can we further simplify this one. And the calculation will be this. Let me rewrite these equations and expand it in the four expressions. And for that one, again, we realize, let me start with this. Tau ij equal to tau 1, 1, 1, 2, 1, 3, and 2, 2, and 2, 3, and 3, 3. Because of the symmetries in stress, so basically here we can only use the 6 stress components will be fully sufficient. Okay, the same thing for strain. So basically here, I want to expand this one. In theory, this should be 9 by 1, 9 components, and 81 components. Using this symmetry can help us to reduce to 6 components, and 6 by 6, 36 components. Okay. So keep that in mind. Then basically that expression will be something like this: tau 1, 1, tau 2, 2, tau 3, 3, and tau 2, 3, tau 1, 3, and tau 1, 2. Okay, that is the 6 components I want to be focused on. Okay, and that is our ordering the sequence. So that means I pick this is the ordering sequence is 1, 2, 3, 4. And 5, 6. So that is the orders I place from this into a column like this. Okay, so 1, 2, 3, 4, 5, 6, like this one. Okay, the same ordering sequence applied to strain. Okay, and with this is for the ordering, and with this in mind, and I want to begin to look at. So this, if we have this stress strain, if we have this stress tau ij equal to say ij kl and epsilon kl, so this one is described in, for example, in terms of this coordinate, this kind of coordinate systems. On the other side, I want to proceed the calculations, for example, ij prime equal to C I J K L prime and epsilon KL prime. With the prime, that means I want to find its corresponding descriptions in the new coordinate system, which is like this. Okay, and then I simply compare the contents here. So that is the kind of thinking strategy. So the remaining calculation simply, essentially, is to implement such a 2 calculations. Okay, and then we see. Let me start with this one. So with the same ordering sequence, I want to see what happens on this one here. Okay, and that is my strategy. According to my notes, I don't want to mess up. You can start with this one, but here for today, I choose start from this one, and then I will go back to this one later. Okay, that's the sequence. So now for this one, then I want to map. I want to map into this one, and from here probably you can see, and tau 1, 1 prime using this notation. Let me keep the notes here. So the relation between the two things is this tau ij prime. Again, using our cosys, not using the transformation stress formula, relating to ij will be I. Let me change the symbols. Ij will be I, Lj, J, tau ij. Okay, I'm going to adopt this formula to implement this one. So the first one, I proceed to tau 1, 1. So for this case, tau 1, 1 prime equal to, okay, we proceed the calculations. So basically that is tau 1 I, tau 1 j, and tau ij. Okay, and then we're expanding, we should have the 9 terms, because that will be involving the ij from 1, 1, 1, 1, 2, 3, and 1, 2, 3, 2, 2, 2, 1, 2, 3, 3, 3, 3, in total 9 terms, right? Good. So now we proceed. for the first term, this one is involving is tau 11, tau 11, and tau L11, L1, tau 11. So now what is L11, L1? So that is this one. Okay, so the first term equal to tau 11. Okay. Then the second term corresponding, that is the L11 and L12 corresponding to Ij here, and so that corresponding is tau 12. Okay, because for this table, tau 12 equal to 0, tau 13 equal to 0. So you can see this one will be number equal to 1, multiply number equal to 0, this will be equal to 0. If you quickly scan over this one, this will be give us to 0. This one will be 0. This one will be how much?
Tau 22.
No, carefully. This one again, per our template, L1 I equal to 2 and L1 J equal to 2. Tau 1 to 1 2, not 2. Okay, so that will be easy to check in getting the. So this is the tau 2. You got it. 2 is here. But here again, this is 0. This is 0. So this one is 0. Okay, and proceed. The whole thing is remain everything. Every other term will be 0 except the first one. So here, after the calculation, the tau 11 prime equal to tau 11. Okay. Any questions about these calculations? Good? Okay. Then let me do one more, and then I will fill up the remaining terms for time savings. So now for the tau 22 prime. So for tau 22 prime, again, we modify this one, 22, and I say per this template, this is the 22 here. Okay. The same thing, we have in total 9 terms. So we can redo these calculations. And this time, let me bring that kind of calculation here a little bit. Ij and 1, 1, 1, 1, 2, 3, 1, 2, 3, 2, 2, 2, 1, 2, 3, and 3, 3, 3. Again, 9 terms. For the first term, basically we're expanding and using this template here. That will be L21, L21, tau 11. This one will be L21, L22, tau 12. And this one L21, L23, tau 13. And carefully, this one will be tau 21, L22, L21. And this L22, L22, tau 22, L23, L22, L23, etc. Okay, you can write it. Okay, now again, we look at the contents of the L. So everything will be 0 except this term. L22 equal to 1, so this one will be equal to tau 22. Remaining will be 0. This will be 0, 0, 0, 0, 0. So the calculation of this one equal to tau 22. Okay, and I don't need to repeat for the remaining, but you can double check. That one will be equal to tau 33. And this one is minus tau 23. And why minus here? Because once you proceed to this term, it's going to involve this element in that calculation. Okay, so that will make the minus. So this one is minus tau. Something like this. Okay. So similarly, similar pattern of transformations applies to string. So for this case, So for this case, let me save the space. For the strength, we have a similar way. Epsilon 1 prime, 2 prime, 3 prime, and 1 3 2 3 prime, and 1 3 prime, 1 2 prime will be equal to epsilon 1 epsilon 2 epsilon 3 and minus epsilon 2 minus epsilon 1 and epsilon 1 2. Okay, so similar pattern. The similar pattern, that means the showing minus sign happen at the same location of the elements here. So now with those things in mind, we can proceed to exercise these contents here. For this one, on the other side, we can write it up. For example, tau 1 prime. Right now, I'm going to apply this one equal to C11 KL prime times epsilon KL. Right? Okay, and so we proceed. So right now, the KL, so basically, only have 6 terms. So due to the symmetry, we just list the 6 terms. Okay, so this one will be equal to, using this one, let me write it up here. Open the space. So therefore, tau 1 prime equal to tau 1, and the first one, so KL, right now I'm going to implement KL number equal to the 6 number here, 1 1 2 2 3 3 and 2 3 1 3 and 1 2. I'm going to pick up only the 6 elements in this model, so that is the labels I'm going to expand. Okay, so tau 1 KL equal to 1 1 epsilon 1 and plus tau 1 2 epsilon 2 prime. Okay, we forgot the prime. And then plus C prime. Okay, and C prime and 1 1 3 3 epsilon 3 prime plus C 1 1 2 3 epsilon 2 3 prime plus C 1 1 1 3 epsilon 1 3 prime plus C 1 1 1 2 epsilon 1 2 prime. Okay, so in here I totally have the 6 terms expanded. Okay, now I have done this one. Now I'm going to transform into this one. I want this term appear for this first element. So to appear, I simply utilize the achievement what we have done here. This one with the replacement of this term. So this one, let me call this equation 2, this equation 1, okay? So this one using equation 2 apply to here. So this one equal to epsilon 1, this one 2. Let me write it out first. This is 3, and this is minus 2, 3. This one minus 1, 3. This one is 1, 2. Okay, that's a replacement using equation 2. So the same thing, the copy is here. Sorry, wrong. Okay, like this. Good. So from this step to this step, I simply utilize this relation. I simply replace the components. And this way I can gradually creep into this description. Okay? Any questions? Good? Okay. Now again, on the other side, I want to describe the relation using this one. So tau 1 in the similar way, tau 1 epsilon epsilon 1, 1 plus C1, 1, epsilon 2, 2, and epsilon 3, 3, epsilon 1, 2, 3, epsilon 1, 3, and epsilon 1, 2, 6 terms. So 2, 2 plus C1, 1, 3, 3 plus C1, 1, 2, 3 plus C1, 1, 1, 3 plus C1, 1, 1, 2. Okay, on the other side, this is the expression from this term. Good. And one more piece I want to utilize is equation 1 here. This one, using equation 1, we know this equal to tau 1, 1. Okay, so that means this equation equal to tau 1, 1. Right? Now we compare this equation describe the tau 1, 1 in relation to epsilon 1, 1, 2, 2. The same thing for this one, which is saying the two equations must be equal to each other, right? Okay. And finally, we're going to impose the symmetry. And here we say the symmetry is such that at the pairs of the symmetric points, their mechanical properties must be equal. So if the two representing is a mechanical relations between the stress strain at the pairs of the symmetric points, if those are associated with the behavior of the materials at the symmetric point, that means mechanical properties must be the same. So which means C ijkl must be C equal to the prime of this one. So that means at the very beginning, I think I'm done the redundant. That means we must use the same mechanical properties to describe the behavior at the pair of the symmetric points, right? So this action, I impose these properties here. Good? Okay, so that means when we imposing the material symmetries, basically this one we can just using the same mechanical properties here. Will be good? Okay. So under everything compared, you can see basically from this comparison, C1, 1, 1, 1 equal to this term trivial, this one equal to this one trivial, this one equal to this one trivial. We'll compare term by term. This one equal to this one, that means C1, 1, 2, 3 equal to minus C1, 1, 2, 3. That's saying these quantities equal to 0. The similar way, we compare this term, so that means C1, 1, 1, 3 equal to 0. Okay? So under these situations, let me see. So let me see. Let me write it up. So tau ij, tau 1, 1, 2, 2, 3, 3, 2, 3, and 1, 3, and 1, 2. This one basically equal to C1, 1, 1, 1, C1, 1, 2, 2, 1, 3, 3, 1, 1, 2, 3, 1, 1, 1, 3, 1, 1, 1, 2. Epsilon 1, 1, 2, 2, 3, 3, 2, 3, 1, 3, 1, 2. Okay, I'm going to write down the whole things at this moment. 2, 2, 1, 1, 2, 2, 3, 2, 2, 2, 2, 3, 2, 2, 3, 2, 1, 3, and 2, 2, 1, 2. patient a little bit. 1, 1, 2, 2, 3, 3. Are you able to figure out the pattern? Okay, smart. Okay, so that is the original, and here, because of the symmetry, again, here, the symmetry here in total only 21 independent parameters we need to use, right? That's the original for anisotropic. Now we impose this plane of the symmetry. As a first step, we compare. Right now, we only proceed the calculation of the 1, 1 component. Then what we achieve is the 2, 0. So I can mark out is this one. What are the 2? Where? 1, 1, 2, 3, 1, 1, 1, 3. This term equal to 0. This term equal to 0. Good? Okay, so now 21 minus 2, we have 19. Good news. Right now, I only proceed is tau 1, 1 element. So are you able to proceed? Now we've done this one already. Then we proceed to the remaining 5. A lot of writings, but I can do that one here. So maybe it will be a good time for you to proceed this kind of calculations. Now we're going to compare these components here, tau 2, 2 prime. Okay, so basically tau 2, 2 prime equal to, again, using that pattern here, will be C 2, 2, 1, 1, epsilon 1, 1 prime plus C 2, 2, and 2, 2, epsilon 2, 2 prime plus C 2, 2, 3, 3, epsilon 3, 3 prime plus C 2, 2, 2, 3, epsilon 2, 2, 1, 2, epsilon 1, 2. Okay. So here again, I have imposed the symmetry properties. That means if a pair of the points, like the transformation using this table, if they are symmetric through that table, then the material properties must be the same. So let me use C as that material properties. So now I'm going to replace prime, this one will be equal to, again, using this table, so that will be the same number here. And this one, the same number here. The same number. And this one will be minus 2, 3 equal to this minus. So minus this number. And minus this number. And plus this number. Okay. On the other side, 2, 2 prime equal to this one. So this one equal to 2, 2. Okay, 2, 2 prime equal to this. Good? Okay. And on the other side, 2, 2, from our expansion here, that is this number, 1, 1, plus this number, 2, 2. That one, this one is just copy from there, and this number, 3, 3, plus this number, 2, 3, plus this number, 1, 3, plus this number, 1, 2. So from here, very quickly, you can identify from this comparison, this component must be equal to 0, right? So 2, 2, 2, 3, this one, and 2, 2, 1, 3, this one. So now we knock down another 2, and then we're going to proceed this one, then we can knock out 4. Good? So I can tell you, the zeros. So after we proceed in the whole 6 sets of the calculation, let me write it up here completely. So this will be C 2, 3, 2, 3, C 2, 3, 1, 3, C 2, 3, 1, 2. This one will be C 1, 3, 1, 3, C 1, 3, 1, 2, C 1, 3, 1, 3. Okay. And yeah, those are the portions here. So after done this one, then that is the whole writing. Then once we complete the whole calculation, those two will be 0, and then the other is the 2 will be 0. Okay, so in total, 21 minus 8 more, that's down to how much? 21 minus 8, 12? No, 13. Okay, so in this way, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yes, 13 dependent parameters for describing a material that exists in a plane of a symmetry like this. Good? Okay. Any questions about this kind of calculation process? So Max, we can take a